these organs, their recording, its pre-processing, and also considered as one of the prime factors to, we can say, diagnose a particular disorder, because human diagnosis, which has been conventionally done in the medical field, has its own disadvantages. This is a conventional method. Of course, it has been followed for many years, and an expert medical practitioner believes that this method is the best, because his individual experience when it goes when a medical practitioner goes through variety of patients, he examines them, he understands their basically he understands the scenario in which a person is affected by a particular disorder or disease, and then he performs further steps of diagnostics decisions and makes the diagnostic decisions. So this has advantages in its in its way, because we cannot deny that this method is not effective. Of course, this method is effective when the medical practitioner himself is experienced. But this is not true in all the scenarios. This is not true in every situation of the healthcare diagnostics, because when situations are about diagnostic decisions to be taken on a very critical and very time dependent disorders, such as if we take an example of the major signal that we learned in this subject, which was electroencephalogram signal. If we take the example of this, we understand that recordings of EEG are quite long. They are complex signals. They are random, non-stationary, and non-homogeneous signals. And such signals have their own impact in the analysis when manually analyzed. For example, a recording of EEG, which is done overnight during the sleep stage, may have huge data recorded in the EEG machine of hospital, and extracting useful information from such a long recording of 8 to 10 hours is a very complex task for a radiologist or a medical practitioner. So in such cases, not all the time, but in few cases, we cannot compute or calculate in how many cases, but there is of course an evidence available in the literature which says that in majority of the cases, these manual diagnostic tests fail. There are many reasons for these tests to fail, and once when the diagnostic fails, all the further medical procedures which are interlinked also fail. For example, if a brain condition diagnosed from EEG signals fails, if the condition diagnosis of the condition fails, the further medication fails. The impact of the medication on patient is not seen, and thus the overall treatment procedure also goes into a wrong direction. Thus, we need computerized techniques, introduction of artificial intelligence, introduction to uh, algorithms which can manually which can assist the manually observed decisions, which can either support or they can also I don't say interfere, but they can also support the decisions which are made manually. If a right decision made, it can assist by telling it's a right decision, and if it is a wrong decision, it can correct the particular decision by using the by making the corrections in the decisions. So this is a very common scenario now, as more and more electronic gadgets have been used in the diagnostics, in the recording of signals, and in the overall process of medical practice. It is necessary for an individual to take into account the positive and negative side of technology and proceed with the methodologies. So there was an aim in this particular subject which was very clear, as the subject was taught to medical professional, Ayurveda medical professionals. It was expected that the complexity of the subject should not go in the engineering direction in terms of mathematics, in terms of derivations, or in terms of programming of the algorithms. It should connect the summary of the core technology to the medical practitioners. So the aim was to teach what engineering background is involved in the process of generation of biosignals from various organs of human body. As such, we have learned mainly three types of signals and their origin the from the chemical composition, that is the cell composition, membrane composition. So the first focus was on this tool, and of course there was a necessity to consider the origin of these signals, as electrical source of these signals was to be understood. Without knowing the electrical source of these signals, it was not possible for us to consider the further process. So unless anyone who takes this course appreciates the signal that is originating from human body has some connection with the electrical composition, and its fundamentals are lying in those base, it would have been difficult for this course takers to appreciate the origin of these signals. So we started with generation of these signals in this course, and we also experienced how these signals originating from various parts of the brain are interlinked. They carry the message from one part of the body to the other part, while they have chemical compositions which do cause the impact on the recording equipment. So there was a need to briefly understand the instrumentation part. So how do we record the signal? How do we capture the signal into the machine? And what are the ways by which these signals can be stored in the memory of computer? So not only the physiological aspects of these signals, such as its origin, chemical composition, etc., but also when it is recorded from deeper organs such as brain or heart, how the impact of these recordings can change the course of action further. That was also discussed in the uh, initial syllabus, that is in the first chapter of this course. Now it was made very clear at later stage that we as a medical practitioner, we are not going to deal or uh, jump in depth into the mathematics part of the signals or the engineering part of this subject, but we will focus only on the aspects which are comfortable for medical practitioners. Therefore, keeping this in mind, uh, f- we decided to proceed on understanding how these signals are useful in automated diagnostics. So we started our journey further in chapter 2 by understanding their physiological signals and their recording methods. So the whole chapter was dedicated to recording these signals, their storage, and also considering how these signals can be communicated with the machine so that the machine can understand those signals for further processing. So that was another aspect of the subject where we focused on various algorithms or various procedures for recording and monitoring these signals. Now, as we concluded in chapter 2, the general procedure of automated diagnostic involves recording of the signals. Before we store them, we need to pre-process because the recorded signal is not always clean and pure as we expect. It is contaminated by noise, as in the process of recording, or by the physiological changes that are impacting the recorded signal. To give you an example here, when we record electroencephalogram signal from brain, the rapid eye movement of a patient can introduce a noise which is called eye blink noise. There can be this is a physiological noise. There can be a noise generated from the electronic equipment used in the process of recording, the electrode, the electrical connections, and the wires which join the electrodes from the brain to the computer system where the recording is done. This variation in impedance is caused by the electrodes to the physical skull can be treated as the external noise. There can be also noise due to the variation in the frequency of the electrical signal supplied. For example, in India, we have 50 hertz AC signal supplied to the equipments. If there is a small variation in this electrical signal, there can be noise introduced from external source. So we had these variety of noises and their detailed study in chapter 2. We further focused on the main aspect of automated diagnostics, and that is feature extraction. Without knowing important information content of the signal, we cannot really make use of these signals into automated diagnostics. So every signal has hidden information, and this hidden information can be extracted through algorithms which are in mainly two domains. I think I should, before I go to the next chapter, I should mention that the signals have been processed in two domains, like time domain and the frequency domain. Of course, today the advanced algorithms have been using the joint time and frequency domain techniques, but we didn't focus on joint time domain methodologies because we, as I mentioned earlier, our aim was not to get in depth into mathematics, but understand the connection between engineering and medical field. So we considered time and frequency domain filtering techniques in chapter 3 and 4. And we dealt more on these filtering techniques because main aim is to filter out these techniques. This was a basic course. So we didn't get into algorithms which extract the information from signal, or we even didn't get into the AI part of automated diagnostics, which starts as a basic machine learning algorithm, and then advancement in the machine learning algorithms. We never focused on this. Yes, but we had a very clear goal of considering the aspects which are important in eliminating the noises introduced in the process of recording biosignals. So in the third chapter, we in fact first made an attempt to talk about various algorithms which are for the biosignals and their connection with the filtering. Biosignals are not filtered directly. They are filtered by considering their existence. So if a recorded biosignal has a duration which is of 5 seconds to 10 seconds, then rather than focusing on the filtering, the focus is more on the feature extraction process. But if the signal, as I mentioned earlier, if the signal is very lengthy, a recording of whole night, 8 to 10 hours duration, then there must be first focus on filtering it rather than extracting features. Because the filtering process includes defining epochs, considering how these filters are affecting the shift variants or shifting domains, transforming a signal from one domain to the other domain and analyzing it for its efficacy is the second parameter. So we studied concepts of Fourier transform in chapter 3, and we learned how these transforms are important in considering the further processes. So overall, when were looking at the algorithms, it was advisable not to get directly into filtering process. First, understand the length of the signal. See, is the filtering really necessary? And then decide on the filtering technologies or filtering algorithms. So for medical professionals who is assisted by biomedical engineer, it is necessary to tell the biomedical engineer that this recorded signal, needs pre-processing, and it has to be filtered for the given duration. So this knowledge, if a medical professional gains from this course, I would consider the success of this course, and that is possible for any medical professional, because the recorded signal, how we see on the computer screen, it will not be the same when we filter it. A lot of noise is removed, the signal strength is improved, noises are reduced, so the signal to noise ratio also improves, and then it gives a very distinct feeling about its appearance on the computer screen. So duration versus the noise removal is the challenging task that has to be dealt in chapter 3. That was dealt in chapter 3. Chapter 4 was more focusing on time domain techniques of filtering the signal. Now, it was assumed that yes, for every recorded signal, the filtering is mandatory. When it is not required, it can be further processed for the feature extraction. But then in the chapter 4 and 5, it was the scenario when we thought that yes, the filtering is essential, and without filtering of this signal, the further processing is not possible. So now, when filtering is mandatory and when filtering has to be carried out, how? In time domain or in frequency domain? That is the question. So this subject deals with stages of signal processing, phase by phase, and it takes into account the stages. It takes into account these stages for few of the calculations, and these calculations do not remain the same for every biosignal. The calculations done for electroencephalogram, that is brain signal, may vary for calculations done for electrocardiogram signals. So let's have a look at third chapter's content. And here I am sharing my screen to show the content of chapter 3. I'm sharing a window of the content. I hope this module is visible. In the module 3, which is linked to module 2, we saw the process of filtering or removal of artifacts, and okay, and it was necessary at that stage in the by the end of module 2, when we enter into the filtering process, which is a major part of this subject. 3 modules are included in the filtering. It was necessary to understand the structure of a noise, whether the noise is physiological, whether it is random, whether it is coming from the external sources, or its occurrence in the signal is stationary, non-stationary, or cyclostationary. So mainly the second chapter was second module was completely on the artifacts, their existence in the signal, and how can they removed from the signal. And that connected us to the chapter 3, which was on fundamental concepts of filtering, either a linear filtering or time domain filtering. If not time domain, if it is frequency domain, then how to go into the frequency domain using Fourier transform. So I did mention in previous lecture, in the regular lectures, that there was some basic and minimal mathematics which is required, which could not be avoided in the entire teaching learning process. Only that much of mathematics was included in the explanation, which was easier for any medical professional also to understand from these concepts. So when we talked about time domain filters, we made a very clear indication of signals on time domain, and these signals, these time domain signals, have either option of averaging. Averaging is a very basic mathematics and statistical method, or derivative based operations for removing or filtering the low pass noises. For noises, there is another word, artifacts, which we have learned in the videos very clearly. So artifacts basically are not something which is continuous in the signal. It may appear for a certain time period. Like example, when EEG recording is happening, the eye blink is not throughout the recording. It may be for certain time period, because immediately the operator who is recording the EEG signal will instruct the patient saying that there is too much of eye movement and you need to control it. So for some patients, it is quite possible for controlling those rapid eye movements. And thus, in such cases, time domain filtering techniques studied in module 4 are greatly useful. Coming to chapter 5 and the last module of this subject, which was more complex rather than time domain filtering, because in time domain filtering, either it was averaging or derivative based approach. But in chapter 5, which we see here, the module 5, which we see here in this part, it was challenging because of two reasons. The first reason was moving from the time to frequency domain. That itself was a big challenge, because when we are willing to remove high frequency signals or high frequency content of the signal, then we definitely need to move from time to frequency domain. And this can be done by using a very well established transform called Fourier transform. Fourier transform not only allows us to enter into frequency domain, do the operation of frequency domain, but inverse Fourier transform allows to take the signal back into its original form in the time domain. And this is possible with low pass Butterworth and high pass Butterworth filters. Butterworth filters have stages, first order, second order, and with the increasing number of stages, more complex information, more deeply hidden information of the signal can be extracted from the filtering process. Now, there are noises which are mixed from all layers of recording stages. The recordings which happen usually at scalp level for EEG signals, or on the surface of the skin for heart signals. The signal which moves from the organ to the electrode tip is influenced by many parameters which it experiences in between, many chemical compositions it experiences, many the material which it experiences. Maybe it's a cell, body, muscle, bone, nerves, veins. Through this journey, when the signal reaches the tip of the electrode, and from there its conversion happens into electrical signal, care to be taken that the analog to digital conversion happens correctly. So in chapter 2, it was also explained how Nyquist criteria plays an important role in deciding the conversion rate of analog signals into digital signal. So a rule of thumb, we can say, is the frequency of the message signal, the signal that we are converting, and the sampling frequency that we use, their relation should be such that the sampling frequency should be greater than twice the frequency value of the recorded signal. Suppose if a recorded beta wave from brain is 2 Hertz, then sampling frequency should be greater than 4 Hertz, which is double than that of 2 Hertz. This is true for every organ, every recorded signal and every uh, physiological electrical signal. So the rule will not change. The algorithm or the theorem will not change for any of this. This is applicable in electronics and communication engineering for communication signals also. When we send signals through mobile phone at a longer distance, when we speak to our friend, or when we send images through email to a longer distance, the frequency of the audio we speak and the carrier frequency, their relation is same. It is greater than twice the value of the original signal. So that was one concept we mainly focused in chapter 2, and we used it further in module 3, 4 as well as 5 as to Nyquist criteria. So that is one thing all of us need to focus while studying this particular course. So overall, when we look at the outcome of this course as designed for this subject, was to understand various physiological biomedical signals, understand different noises. That was the main thing. Signals we can understand based on their origin, how they are generated, how they travel, but noises cannot be studied so easily because source of noise is random. Even head shake, when the electrode cap is placed, can cause physiological noise. So movement of head is not something which can be studied because it's a random process, and we really cannot predict by what angle, with what force the head shake is going to happen, or the rapid eye movement is going to happen. So it's important to understand the fundamentals of these noises, physiological noises and external noises, electrical noises. Study the basic filtering methods. That was our next objective, or next outcome in line with the objectives. The fourth result of this course is to understand time domain filtering techniques, its specifications, how averaging works, and how the derivative based approach works in given scenario. And the fifth outcome was to understand what is the impact of frequency domain filtering techniques and their specifications. So with these objectives and outcomes, we feel that the course uh, has successfully delivered the designed content, and it has made an attempt to create an awareness about usage of tools and technologies of engineering into medicine, where if this happens, there can be a great collaboration between the engineering and medical field, and more productive patient outcomes can be seen, which were not seen in the earlier days. So I thank all the listeners. I thank all the medical professionals who have taken this course and shown keen interest in this subject. Now I'm open for questions, if any. You can post them into chat box. I'll be free to answer them. I'm also sharing my email ID. Here. So anybody has questions, they can feel free and get the doubts clarified. I also wish all the best for the final proctored exam of this course. Thank you. If any questions are there, we can answer them.